Unmute. You hear me now? All right. Cool. So yeah, I'm going to talk about this work on characterizing learnability for stochastic noisy bandits. This is joint work with Wang. So the setup here is supposed to be analogous to the pack model, but we're going to study bandit learning instead of classification. So there's some set of arms, call it pi. It's an arbitrary non-empty set. It's most interesting in this theory if that's an infinite set. There's some function class f, which is a set of functions just mapping arms to values between 0 and 1. It's sort of like a concept class in pack learning. There's an unknown reward distribution, m star. This maps arms to distributions over 0 to 1. In this literature, that's called a model. And then the mean reward function is just the expected value of the reward for any given arm. And the assumption, the only assumption in this work, is that the mean reward function is in the function class. So this, we'll call this a model that satisfies that, realizable with zero mean noise. So the actual learning protocol here, there's an algorithm that's possibly randomized, and it goes in rounds. On each round, it chooses an arm, pi t, from the set of all arms, and sort of pulls this arm, which just means it's going to receive a reward sampled from the distribution, the reward distribution at that arm. After some number of rounds t, it's going to halt and return some arm, pi hat. And we'll say the function class f is learnable in the bandit setting with arbitrary noise if for any alpha and delta bigger than 0, there is an algorithm and a finite value t such that for all models that are realizable with zero mean noise, the algorithm pulls at most t arms and with probability at least 1 minus delta returns an arm pi hat that's at most alpha worse than the max mean reward. The mean reward of pi hat is at most alpha smaller than the max. This is sort of a pack-like formulation. I'll mention all of the results that I'm going to talk about can equivalently be stated for the sort of no regret setting that some of you may be more familiar with. So no regret learnable if and only if it's learnable in this sort of pack sense. Okay. So several specific function classes have been studied quite a lot. But in terms of sort of general theories, there have been some approaches, but no complete characterization as of yet. There was this paper by myself and Liu Yang at Colt 23, which studied the noise-free case and showed a kind of negative result regarding the possibility of a general theory. So we showed that in the noise-free setting, there exists an explicitly defined function class such that bandit learnability of that class can neither be proven nor disproven from ZFC. So this sort of intuitively means that in the noise-free case, there cannot be a simple characterization of bandit learnability. So that's sort of the starting point of our present work. And at the end of that paper, we asked a question of what about noisy models? So that was the noise-free setting. But if we allow arbitrary zero mean noise, what's possible? And in the present work, that's what we study. And we in fact find a very simple characterization of bandit learnability with arbitrary zero mean noise. So what is that characterization? Something called the generalized maximum volume. It's defined like this. So define this gamma quantity as the soup over all distributions on arms of inf over functions in the function class of the probability that if you sample from that distribution p, you get an arm that's at most alpha worse than the max. So it's sort of a very simple, almost obviously sufficient at least quantity. And we indeed show that any function class is learnable with arbitrary noise if and only if gamma is non-zero for all alpha. This builds on some definition from that 2023 paper. There we were just looking at binary noise-free rewards. and we had something called maximum volume, and this is the generalization to real-valued functions. And I'll also mention we've recently noticed this paper at NeurIPS that independently obtained some similar results to this theorem. Okay, so let's look at the sufficiency and necessity of sides of this separately. So sufficiency is actually super easy. I'm sure most of you have already done it in your head. So if you let P be the distribution that achieves this max, just sample about 1 over gamma arms from this distribution. One of them is going to be alpha close to optimal, and then just sample, like pull each of them about 1 over alpha squared times. You get a uniform estimate of their mean rewards, and just return the arm from among these that has maximum empirical average reward. So that works. It's kind of obvious, in fact. The necessity side is more interesting and a little trickier. So here, so that was a sort of order 1 over gamma upper bound on the query complexity. For necessity, we'll show like a log 1 over gamma lower bound. So let's start by assuming f is learnable and let a be some algorithm that learns, and let t be its query bound. Now we need to define a distribution p to witness a lower bound on gamma. So here's how we'll define it. Let's run the algorithm, and each time it pulls an arm, just give it an independent Bernoulli 1/2 reward. Okay, and define p to be the distribution over the pi hats that it returns at the end. Let's analyze it. So for any function in the function class, remember that the values of f are between 0 and 1. So we know there is some model that has mean f and just uses distributions supported on 0 and 1, so just binary valued rewards. So if we consider running the algorithm under one of these distributions, say mf, by the fact that this is a successful learning algorithm, we know with probability 1 minus delta, the algorithm returns a pi hat whose reward under f is at most alpha suboptimal. And we also know with probability 2 to the minus t, all of those Bernoulli 1/2s agree with the rewards that you got under mf. And notice these are independent. So if we just sample from p with probability 1 minus delta 2 to the minus t, both of those happen. So the probability that a random pi from p has a reward f of pi under f that's at most alpha smaller than the max is at least 1 minus delta times 2 to the minus t. If we minimize over f, we get that gamma is at least 1 minus delta times 2 to the minus t, or equivalently, the query complexity of the algorithm was at least log 1 minus delta over gamma. So that's the necessity side of the proof. We have a couple extensions in the paper as well. So in one direction, we extend to broader families of noise. So we allow unbounded noise with bounded variance. In the other direction, we consider some restrictions of the noise, which is interesting in lower bound cases. So the restriction to binary noise, well, that we actually just proved that. We also show you can restrict to Gaussian noise, which a lot of people like. That involves sort of discretizing the distribution in appropriate ways in the context of that proof. And basically, yeah, a lot of other natural noise models, any reasonable noise model you could imagine, this characterization will hold, except, of course, noise-free, where we know you can't have a characterization. Okay, so we showed a log 1 over gamma lower bound and a 1 over gamma upper bound. Is there some hope to close this gap? Well, it turns out not. So in fact, we show that any value between log 1 over gamma and 1 over gamma can be an optimal query complexity for some function class. So if you wanted to formulate a sharp query complexity characterization, you'd have to introduce some refinement of the gamma quantity itself. As an interesting aside, we also show there are function classes So notice that the upper bound, the 1 over gamma, was achieved by a non-adaptive algorithm. It chooses the arms, it chooses what to pull, and then it just looks at the rewards and does decides what to output at the end. You could also imagine adaptive algorithms which sort of adaptively adjust where they query based on what they observe. So the 1 over, we show there are classes where adaptivity is really necessary to get the optimal query complexity, in particular where any non-adaptive algorithm has 1 over gamma, even though there's an adaptive algorithm that gets log 1 over gamma. Thanks.
So for like actual function classes, like let's say like linear contextual, like linear bandits, what is the value of, like how does gamma scale with the dimension?
Right, so for linear function classes, or for linear bandits, it's alpha to the minus d. It's the same for Lipschitz. For Lipschitz, that's tight. For linear, that's quite suboptimal. And so that, like, linear is one of those cases where log 1 over gamma turns out to be the right answer.
Okay. So does that suggest that, like, you, based off the function class, there might be a better dimensions, like?
Right.
Yeah,
So that's sort of what we're trying to get at with this. Is if you wanted to refine the query complexity, you're going to need to replace gamma with some more refined quantity. We sort of chip away at that a little by defining a sort of a variant of the DEC, that's the decision estimation coefficient, that's appropriate for arbitrary zero mean noise in the paper. We don't show it's optimal or anything, but it does seem to have some, the algorithm based on it does seem to have some adaptivity properties that are useful.
That was going to be my question as well. Like, can you elaborate, like, between, like, on the relationship between the DEC and this gamma?
Right. So, yeah. So I mean, the original DEC has a lot of stuff in it with like Hellinger distance. So it's more model based, and so it's going to have, there will be some model classes where it's not characterizing learnability because the realizable ones, yeah, so just because of that dependence on the distributions and sort of being able to estimate distributions and things like that, it's not, that can't recover our results, but we do formulate a variant of it where instead of distribution estimation, we base it on mean estimation, and we replace they have an expectation in the objective, and we replace that with a probability that's sort of more like the gamma quantity. So it's sort of, if you put a constraint in this probability to be close in mean, you get a variant of the DEC.
Maybe you can say another word about this other New paper by Sasha, and like, what is their definition and what is yours? Because
It's the same.
it's the
Same definition, yeah.
Right, so
Yeah. So that was, I think the alt submission deadline was after or before the paper appeared, so we just didn't know about it.